The first approach that we consider for estimating the total capacity of a battery cell is a Kalman filter-based approach. So everything that we learned back in Chapter 3 is now going to be applied in a different context where we were looking at estimating a state of a model before, and now we are looking at estimating parameters of the model. So we know that the Kalman filter may be used to estimate the state of some dynamic system if we know the parameters and if we have noisy measurements. It turns out that we can also use nonlinear Kalman filters to estimate parameters of our model if we have a known state and noisy measurements. It's also possible to do both. So first we are going to consider in this section of notes and the next topic how to estimate the parameters of a system if the state is known. And so the big assumption is somehow I know the state of the system. I'm not estimating it. I've got perfect knowledge of what the state is, the state of charge, the diffusion currents, all of that. But we don't. In practice, we don't. So in practice, we need to do both of these at the same time. So we consider how to estimate both the state and the parameters simultaneously using two different approaches. We look at here at a generic approach to parameter estimation that fits inside of the nonlinear Kalman filter framework. And we've got a collection of parameters. We've got maybe coulombic efficiencies and resistance and the other resistances and capacitances and hysteresis magnitude. We've got a whole bunch of things that we might want to estimate. And we are going to put all of these parameters together into a vector quantity called theta. And so the true parameters are theta. Estimates are going to be theta hat. And we will use a Kalman filtering technique to estimate these parameters, just like we've estimated the state. So that means a Kalman filter requires, remember, a state equation and a measurement equation. Here the state equation is really, maybe we should call it a parameter equation, because it's talking about how the parameters can change with time. We could come up with super sophisticated mathematical models of degradation of cells and put those in and say, well, this parameter changes because of SEI growth, this parameter changes because of lithium plating, this parameter changes because the positive electrode is decomposing, etc., etc., etc. We could have very complicated models. But it probably wouldn't help us an awful lot for this application because the time constants of those changes are so slow that they are, the models would probably be dominated by any kind of measurement noise, and the model wouldn't help us a lot. We can get away with a very simple model of parameter changes. And this model is often used. It's saying that the true parameters of the system right now are equal to the prior parameters of the system plus some forcing function. In our model, we say this forcing function, the forcing function is what's causing the parameter value to change. We model it usually being some completely fictitious random noise. Mind you, we don't add the noise in the model, but remember the Kalman filter takes into account process noises, so this is a process noise, to allow the filter to adjust the parameter estimate. So if R was exactly 0 in this case, the Kalman filter would say, I can't change the parameter because it doesn't change. The model tells me it never ever changes. But if R is modeled as some noise source with some just very small noise, then the Kalman filter says, oh, this parameter could change and I need to consider that when I am updating my vector of parameters. And so the bigger the covariance of R, the more the common filter thinks that parameter can change, and the faster it will tend to update it, but it will also be a noisier update too. So for a parameter estimation problem, the covariance of R is usually chosen to be very small so that the common filter is able to adapt the parameter, but not too quickly, so we have a smooth update. So again, R is fictitious. We never actually add it to our parameter we don't generate random noise and add it to our parameter in the common filter. The common filter steps, however, do account for this being in the model to allow adaptation to the parameter. As you go back to the model equations, you can notice that. And I believe, I don't have it handy right now, but I believe I have tables of the algorithms in the appendix of this chapter for you to review how that works. So we need, for any kind of common filter, we need a dynamics equation, which we previously called a state equation. Now we might think of it almost as a parameter equation. We also need a measurement equation. So somehow we have to be able to measure something physical that reflects in some way a change in a parameter value. Here we have a kind of a generic measurement d sub k, which is some nonlinear function h evaluated at the present state of the model, the present input to the model, the parameters of this cell, and some measurement noise ek. So h is an output equation. It could be the same as our voltage equation from our enhanced self-correcting cell model. That would actually be okay, and it's probably what we would do. But I write it here a little bit more generically because maybe you come up with some clever measurement that's not simply voltage that you could use to correlate against a parameter change, and so you would want to put your own function in here instead. So dk may be equal to, may space be equal to our measurement voltage yk or vk, I think we sometimes called it, but it may not be. That's what we say here. This variable here, remember what we did last chapter is we said I would use this fancy font to indicate a collection or a set of measurements. So fancy dk is the collection of all measurements from time 0 up to time k, and we will use that notation. And the ek, the sensor noise here, may be the same as the vk sensor noise we considered last chapter. This is not voltage, by the way, it's noise. They often play the same role, but they might be different. So I'm using a different letter just in case. And when I'm looking at the system dynamics, so these are the parameter dynamics. Those are distinct. So I've got theta k plus 1 equals dot dot dot. That's one equation. And then I've got, what did I call it? dk equals dot dot dot. This is the model of how the parameters change. I also consider a model for how the state changes. So the new state is the state function times the old state, the old input, the system parameters, the process noise. The old output voltage probably is some function of state, input, parameters, and sensor noise. What we changed here versus last chapter is adding the parameters in explicitly because those were not written in the equation before, but now we have to start considering them in the equation because we're saying that they could change with time. So any time varying numeric value in the model we would put in theta. Any non-time varying numeric value, any strict constants, we can simply embed within f and h, and we don't estimate those. So if our sample period is always 1 second, our delta t would always be 1 over 3600. We don't estimate that. We just put in the 1 over 3600 in the model, for example. Okay, so those are some preliminaries. what we're going to do is we're going to apply extended common filter and sigma point common filter to those equations, the parameter equations, to estimate parameters. It turns out that adapting the SPKF to this kind of equation is fairly straightforward. As straightforward as SPKF can ever be. I understand it's challenging to understand that at first, but once you understand SPKF, applying it to parameter estimation is just following the steps. Extended common filter, applying that to parameter estimation is a little bit more tricky though. So we're going to reserve a whole topic for discussing that, and we'll do that in the next topic area. Here we look at SPKF. Remember SPKF, I define sigma points, these vectors, a set of vectors rather, where each vector is by itself kind of like a possible random outcome of your quantity that you're modeling, but together as a set, they describe overall the randomness of whatever you're modeling. So the mean of this set is the expected value of the random variable, and the covariance of this set is the covariance of the random variable. And so we put together all of the randomness in an augmented vector, just like we did when we looked at augmented states before. We have the randomness of the parameters that are unknown. We have randomness of sensor noise that's unknown. The randomness of the driving process noise that's unknown, maybe. Whatever randomness we need to model, we put together in this augmented vector in different sections. And then we'll see how that impacts the 6 steps. So we're going to look, as always, at the 6 steps of sequential probabilistic inference and adapt them to a sigma point common filter methodology for estimating the parameters. So remember step 1a, I'm trying to predict the present parameters given only past measurements. So by definition, this is saying theta hat. So hat because this is a prediction, it's not the true thing. So theta hat at time k of the augmented parameter vector with the minus to say this is a prediction and not an estimate is equal to, by definition of the step 1a process, it's the expected value of theta at time k given dk minus 1, and our model says the expected value at time k, or sorry, the theta, you say theta at k in our model is equal to theta k minus 1 plus r k minus 1. That's what our model said, so we stick that in. And we take the expectation of this, and assuming that I've got 0 mean sensor noise, or not sensor noise, process noise, this simply gives me the expected value of theta given past measurements, which is the past estimate of my augmented parameter value. So step 1a is trivial. It says the parameter prediction at this point in time is equal to the previous parameter estimate. I don't do any computations at all. And I think this makes sense. The parameters are assumed basically to be constant, except for this small fictitious noise that could drive the parameters around a little bit, but there's certainly no kind of a deterministic known trend to the parameters from one time instant to the other, so we predict the present parameters to be the previous estimated parameters. The next step in sigma point common filter, if you remember, is to compute the covariance of the prediction error. And to do that, we first compute an equation, not compute, but we derive an equation for the prediction error itself. So prediction error is equal truth minus prediction. The truth is this, the prediction is that. I combine that thing and that thing to get the previous estimate error. So the prediction error equals the estimate error plus the driving noise. And that should make sense. I said that the prediction is equal to the estimate, so whatever error I had before just propagates through, And then the driving noise was not part of my step 1A, so that would add to the error in my prediction. We want the covariance of the prediction error. I see that I have an error here. Sorry. That should be a minus. So the prediction covariance is equal to the expected value of the prediction error times prediction error transpose. And I put in what that equation is in two places. And if we assume that the prediction error is uncorrelated with the random driving noise, which it would be, there's no reason to say that this fictitious noise has any knowledge of my prediction error up to this point, and the driving noise R is zero mean, then those go away, and I end up with the prediction error covariance or uncertainty equals the previous estimation error uncertainty plus the added uncertainty of this fictitious driving noise, this process noise. Okay, so when I'm making a prediction, I just use the old estimate, but we understand that the parameters may have changed, and so the uncertainty of my prediction needs to be bigger than the uncertainty of the estimate. By how much? Well, by how much those parameters might have changed. So this is going to be a tuning factor in the prediction the state parameter estimation update is how big that covariance should be. And it should probably be quite small because we're saying that quite small changes can happen only to this parameter vector, but it can't be zero. If it's zero, then I'm not going to adapt in my filter the way that I want to. Next step is to estimate, or predict rather, the system output, and this might be voltage, might not be voltage, but here I'm thinking about it as voltage. So to predict the output, we require a set of sigma points that somehow describe the randomness of the uncertain parameter vector, and then to compute the output for each sigma point, and that would overall give me the expected output and the uncertainty of the output. So I create sigma points describing the prediction, and those sigma points I'm going to give the name script W. W, I'm thinking, I know I don't have a calligraphic font for theta, so I can't just do that. So I'm thinking of W as weights, weighting factors in the model. So that's why I chose W. So W, the sigma points that describe the prediction, is the mean prediction, the mean plus the scaled Cholesky factor, the mean minus the scaled Cholesky factor. There's really no difference here between what we've done before. If you understand that, you should understand this. We just have a collection of data that together describe the mean and covariance, the uncertainty of the prediction. Then we take each one of those resulting sigma points W, and we break it into the parameter part and the modeling error part, and we propagate these parts through the output equation, and we compute then different outputs, different sigma points, dki, for time step k. That means that any one of these output sigma points is the output function evaluated at the known, precisely known state, the precisely known input, the sigma point for theta, and the sigma point for the sensor noise. So I get this collection of output sigma points, and I compute the output estimate, d hat, as the expected value of that, and remember that we did that by weighting a summation of the output sigma points. So no change really between this and between what we've seen before and this. Step 2A is to estimate the gain matrix. We just called it LK before. Now I'm going to call it L theta K because we remember that this is the gain for the parameter estimator filter. later on we're going to have a state filter and a parameter filter, and I want to be able to distinguish between them, so I give this one a different name, L theta. We have to compute the autocovariance of the output. We do that exactly as we did before. The cross covariance between the parameters in the output, we do that exactly the same as before, and then we compute this gain as the first matrix times the inverse of the second matrix. So there's really no change in the process. We just use the D variable and the W variable this time as opposed to the X and the Y variable, which is what we would have done in a state filter. Well, I'll try to make these changes to the notes. So this is a parameter estimate update, and copy paste has hurt me here. So our next step is to compute the posterior parameter estimate by updating the a priori prediction using the estimator gain and the output prediction error. So this here, the step is exactly the same as before. And finally, we do the error covariance measurement update, where we just use this optimal formulation as before. So it's a straightforward application of SPKF to a new problem. We basically changed some of the variable names, and that was the biggest change. The other change, if you noticed, if you're following along really carefully, you noticed in step 1a that because the parameter equation is linear, I don't have to create augmented parameter vectors in step 1a and so forth. I can just do the optimal formulation directly. So step 1a and step b boil down to the same thing we would do in a linear common filter, because the equation there is linear. And it's only later on when we get to the nonlinear bits that we have to rely on the nonlinear formulation of the SPKF. Well, with that introduction, I think we're also ready to look at extended common filter, which is a little bit tricky if you're not really paying close attention. So we're going to pay attention and try to do it right, and that's what we do next.